about concept of energy changes and relating them to chemical reactions. All right, we've seen about balancing equations before and states and things like that, but one thing we haven't seen before is energy evolved or taken in or anything like that. So I just want to touch on this a little bit. So basically there's two different sorts of reactions. Ones that give energy out and then ones that take energy in. Some reactions give energy out to the surroundings, that means they get hot. Some reactions take energy in from the surroundings, which makes them cold. Alright? So for example, the reaction of aluminum with iron oxide to form iron and aluminum oxide. This is a this reaction gets very, very hot very quickly. You mix these two together, start the reaction off, and it gives off so much heat that this is the reaction that's used to weld railroad ties together when you're making railway tracks. So this literally makes molten iron that falls through the bottom of your reaction mixture and falls into a blob that you can then shape into the link between parts of a railroad. Now, the way that's represented is when the aluminum iron and iron 3 oxide react and give off iron and aluminum oxide, a whole bunch of energy is given out. So usually we talk about energy in terms of kilojoules. We could talk about it in terms of calories and joules, but we're going to focus on kilojoules. When 2 moles of aluminum react with 1 mole of iron oxide to form 2 moles of iron and 1 mole of aluminum oxide, you get out this enormous 850 kilojoules of energy, of heat. This is what's known as exothermic. Energy is given out. All right? Exo means outside, like an exoskeleton is one on the outside. All right? And when you talk about energy being given off, we use this energy term here, it has a negative sign. Now what that means is these reactants have lost this much energy when they react. Alright, that's what the negative sign is for. A negative sign means an exothermic reaction, one that heats up, one that gives off heat. On the opposite side is an endothermic reaction. Endoskeleton, like the one we have inside our bodies, means endo on the inside, or takes in. A reaction like water, decomposition of water to give hydrogen and oxygen, it doesn't happen by itself. You have to put a bunch of energy in to make it happen. So whereas this reaction just happened and gave a bunch of energy out, this reaction needs a bunch of energy to put in before it will actually go. It gets that energy from the surroundings, which makes it cold. All right. So an energy sign that's positive means an endothermic reaction, one that takes energy in from the surroundings. If you were to have a flask with this reaction in it and stuck it on your hand, it would feel hot. Actually, this one would burn through your hand, but anyway, the point is it would feel hot. If you have a flask with this reaction in it, it's endothermic, it pulls energy in from the surroundings, it would feel cold. Now let's actually do an example of a reaction where we can calculate an amount of energy produced from a number of grams started off with. Let's look at the reaction between nitrogen and hydrogen to make ammonia. Now you've always got to make sure that if you have an equation like this, you've got to make sure either it's balanced to begin with, or if it's not, you've got to balance it. So let's balance it. 2 nitrogens here, 1 here, let's put a 2 here. That gives us 6 hydrogens here, we've got 2 here, so we'll put a 3 here. That actually balances everything out. So what this says is when we take 1 mole of nitrogen and react it with 3 moles of hydrogen to give 2 moles of ammonia, we get out, or we have an energy change of negative 922 kilojoules. Now remember what we said before? Negative means exothermic, so that energy is given out. This will get hot, this will warm up. Energy is being released. In fact, the question tells us that. So it says how much heat is released from the production of 75 grams of ammonia. Well, we need to figure out some conversion factors here. And so the question tells us that we're dealing with ammonia. Ammonia is our NH3 here. So somehow we have to find a way to go from grams of ammonia to kilojoules. All right, and we know we're going to start with 75.0 grams of ammonia. Now, what we said before is still true. 1 mole of nitrogen gives you, and 3 moles of hydrogen gives you 2 moles of ammonia. So what that means is then, for every 2 moles of ammonia that get produced, you have this energy change. Alright, this amount of energy is given out for every 2 moles of ammonia that gets produced. And we can actually use that in our conversion factor. Alright, so you can see that this relates moles to kilojoules. But if we want to use this, we have to get to moles first. Now, we've seen this before. We can go from grams to moles using the molar mass of something. So 1 mole of ammonia. 1 mole of ammonia. Nitrogen's, what the hell is nitrogen? Nitrogen's 14, hydrogen's 1, so I'm just going to say 17 grams of ammonia. I'm just rounding here. So this takes us from grams to moles. And then we have to go from moles to kilojoules. Now we know we have to end up with kilojoules, so I'm going to put kilojoules on the top here. Now the important thing to remember is that's 922 kilojoules for every 2 moles of ammonia formed, not 1 mole. And if you ask yourself, well, why is it 2 moles of ammonia? Well, it's 2 moles because of the balanced equation. Hence why balancing the equation is super important. Alright? Now, of course, if I was prepared, I would have calculated this bloody thing already, but because I'm not, I'll do it right now. So 75.0 grams divided by 17 gives us that, times negative 922 divided by that, gives us an answer of negative. Now remember, you got a positive number, a negative number. Your answer's got to be negative. If it's not, you've screwed up somewhere. And it's going to be quite a big number because 922 is a big number itself. Negative 2033.8 kilojoules. So what that means is, for every 2 moles of ammonia that gets produced, 2033.8 kilojoules of energy is given out. But what if we had to show this to 3 significant figures, because that's 3 here? Well, that is just negative 2030 kilojoules. All right, but that's how we get to the answer, and that is how you relate energy and chemical reactions together. All right, thank you.